Hello everyone, welcome back to the channel. In today's video, we are going to understand one of the most important concepts in pumping systems, the system curve. The system curve tells us how much head is required by a piping system at different flow rates. It is one of the key factors in selecting the right pump and determining its operating point. But before we draw or understand the system curve, we first need to understand the pumping system itself and the different types of heads acting in it. So, let's begin with this diagram. As you can see, this is a simple pumping system. On the left side is the suction tank, which contains the liquid to be pumped. At the bottom is the pump, driven by an electric motor. The pump draws liquid from the suction tank through the suction pipe and delivers it through the discharge pipe. On the right side is the discharge tank, where the liquid is finally delivered. The horizontal dashed line passing through the center of the pump is called the datum or pump center line. It serves as the reference level from which all vertical heights are measured. Now, let's look at the vertical arrows shown in the figure. The vertical distance from the datum line to the liquid level in the suction tank is called the static suction head. Similarly, the vertical distance from the datum line to the liquid level in the discharge tank is called the static discharge head. The vertical distance between the liquid level in the suction tank and the liquid level in the discharge tank is called the total static head. So, this diagram introduces the three important heads in a pumping system: static suction head, static discharge head, and total static head. Now that we understand the layout of the pumping system and these head definitions, let's see how these heads, along with friction losses in the pipeline, combine to form the system curve. Let's understand the different types of losses present in a pumping system. These losses can be broadly classified into two categories: static head and dynamic head losses. Let's start with static head. Static head is the head required to lift the liquid due to the elevation difference between the suction liquid level and the discharge liquid level. In simple terms, it is the vertical height through which the liquid must be pumped. One important point to remember is that static head is independent of the flow rate. Whether the pump is operating at a low flow rate or a high flow rate, the static head remains constant because the elevation difference between the two liquid levels does not change. Now, let's move on to dynamic head losses. Unlike static head, dynamic head losses increase as the flow rate increases. These losses occur because the flowing liquid experiences resistance while moving through the piping system. Dynamic head losses consist of two components. The first is pipe friction loss. This loss is caused by friction between the flowing liquid and the inner surface of the pipe. As the liquid flows through the pipe, a portion of its energy is lost in overcoming this friction. The second component is minor losses. These losses are caused by pipe fittings and components such as valves, elbows, T's, reducers, strainers, and other fittings. As the liquid passes through these components, the flow direction or velocity changes, creating additional resistance and resulting in energy loss. Now that we've understood the different types of losses in a pumping system, let's see how they are represented mathematically. The total head loss in a pipe system due to flow resistance can be expressed as the sum of the static head, friction head loss, and minor head loss. This can be simplified into the following equation. H is equal to H sub S plus K multiplied by Q squared. Let's understand what each term represents. H is the total head loss required by the system. H sub S is the static head, which is the elevation difference between the suction and discharge liquid levels. K is the resistance coefficient. This coefficient represents the overall resistance offered by the piping system and depends on the pipe geometry, pipe fittings, and friction. Q represents the flow rate. Now, Let's look at the equation used to calculate the resistance coefficient, K. The resistance coefficient depends on several parameters. F is the Darcy friction factor, which represents the friction between the flowing liquid and the pipe wall. L is the pipe length. D is the pipe diameter. A is the pipe cross-sectional area. G is the acceleration due to gravity. And sigma K sub m represents the sum of all minor loss coefficients, which accounts for losses caused by valves, elbows, T's, reducers, strainers, and other pipe fittings. By combining all these parameters, we can determine the resistance coefficient, which is then used to calculate the total head required by the pumping system. This simplified equation provides a convenient way to estimate the total system head by combining the effects of static head and flow-dependent resistance losses. Let's focus on this HQ graph. On the horizontal axis, we have the flow rate, Q. On the vertical axis, we have the system head, H. Notice that all three curves start from the same point on the vertical axis. This point represents the static head, HS. As the flow rate increases, the required system head also increases. However, it does not increase in a straight line. Instead, the curve bends upward, forming a parabola. Now, let's compare the three curves. The blue curve is the flattest curve. This represents a system with low resistance. As the flow rate increases, the required head increases gradually. The green curve represents a system with medium resistance. Compared to the blue curve, the required head increases more rapidly for the same increase in flow rate. Finally, the red curve is the steepest. This represents a system with high resistance. Even a small increase in flow rate requires a much larger increase in system head. So, moving from the blue curve to the green curve and then to the red curve, we can see that the slope of the system curve becomes steeper. In simple terms, a flatter curve indicates lower system resistance, while a steeper curve indicates higher system resistance. This graph clearly shows that as system resistance increases, the HQ curve becomes steeper, and as system resistance decreases, the HQ curve becomes flatter. Effective pipe length, L, on the system HQ curve. Now let's see how pipe length affects the system HQ curve. In this graph, the x-axis represents the flow rate, Q, and the y-axis represents the system head, H. The graph shows three system curves corresponding to short, medium, and long pipe lengths. Notice that all three curves begin from the same point. This indicates that the static head is the same for all three cases. The only parameter changing is the pipe length. Let's begin with the blue curve, which represents the short pipe. Because the pipe is short, the water travels a shorter distance. As a result, friction losses are lower, so the required system head increases gradually with flow rate. This produces the flattest curve. Now look at the green curve, which represents the medium pipe length. Since the pipe is longer, the fluid experiences more friction. Therefore, for the same flow rate, the system requires more head than the short pipe. As a result, the curve becomes steeper. Finally, observe the orange curve, which represents the long pipe. Here, the fluid travels the greatest distance, producing the highest friction losses. Consequently, the system requires the highest head for the same flow rate, making this the steepest curve. For example, if we compare all three curves at the same flow rate, the required head is lowest for the short pipe, higher for the medium pipe, and highest for the long pipe. Therefore, we can conclude that increasing the pipe length increases the friction losses, which makes the system HQ curve steeper. In simple terms, a longer pipe requires more head to deliver the same flow rate. Effect of pipe diameter, D, on the system HQ curve. Now let's understand how pipe diameter affects effect of pipe diameter, D, on the system HQ curve. Now let's understand how pipe diameter affects the system HQ curve. In this graph, the x-axis represents the flow rate, Q, and the y-axis represents the system head, H. The graph shows three system curves corresponding to large, medium, and small pipe diameters. Notice that all three curves start from the same point. This is because the static head remains constant. The only parameter changing is the pipe diameter. Let's begin with the blue curve, which represents the large diameter pipe. A larger pipe diameter allows the fluid to flow with lower velocity. Lower velocity results in lower friction losses. Therefore, the required system head increases slowly with increasing flow rate, making the system curve the flattest. Now look at the green curve, which represents the medium diameter pipe. Since the diameter is smaller than the blue case, the fluid velocity increases. This leads to higher friction losses, so more head is required for the same flow rate. As a result, the system curve becomes steeper. Finally, observe the orange curve, which represents the small diameter pipe. Here, the fluid flows through the smallest pipe, producing the highest flow velocity and the greatest friction losses. Consequently, the required system head increases rapidly with flow rate, making this the steepest curve. If we compare all three curves at the same flow rate, the required head is lowest for the large diameter pipe, higher for the medium diameter pipe, and highest for the small diameter pipe. Therefore, we can conclude that increasing the pipe diameter reduces friction losses and makes the system HQ curve flatter. In simple terms, a larger pipe diameter requires less head to deliver the same flow rate, whereas a smaller pipe diameter requires more head. Effect of pipe cross-sectional area, A, on the system HQ curve. Now let's understand how the pipe cross-sectional area affects the system HQ curve. In this graph, the x-axis represents the flow rate, Q, and the y-axis represents the system head, H. The graph shows three system curves corresponding to large, medium, and small pipe cross-sectional areas. Notice that all three curves begin from the same point. This indicates that the static head remains constant. The only parameter changing is the pipe cross-sectional area. Let's begin with the blue curve, which represents the large cross-sectional area. A larger pipe area allows the fluid to flow at a lower velocity. Lower velocity results in lower friction losses and lower minor losses. Therefore, the required system head increases gradually as the flow rate increases, making this the flattest curve. Now look at the green curve, which represents the medium cross-sectional area. Since the pipe area is smaller, the fluid velocity increases. This causes higher head losses, so more head is required to achieve the same flow rate. As a result, the system curve becomes steeper than the blue curve. Finally, observe the orange curve, which represents the small cross-sectional area. Here, the fluid flows through the smallest area, producing the highest velocity. Consequently, the friction losses are the greatest, and the required system head increases rapidly with flow rate, making this the steepest curve. If we compare all three curves at the same flow rate, the required head is lowest for the large area pipe, higher for the medium area pipe, and highest for the small area pipe. Therefore, we can conclude that increasing the pipe cross-sectional area reduces flow velocity, decreases head losses, and makes the system HQ curve flatter. In simple terms, a larger pipe area requires less head to deliver the same flow rate, whereas a smaller pipe area requires more head. effective minor loss coefficient, sigma K minor, on the system HQ curve. Now let's understand how the minor loss coefficient affects the system HQ curve. In this graph, the x-axis represents the flow rate, Q, and the y-axis represents the system head, H. The graph shows three system curves corresponding to low, medium, and high values of the minor loss coefficient. Sigma K minor. Notice that all three curves start from the same point. This indicates that the static head remains constant. The only parameter changing is the minor loss coefficient. Let's begin with the blue curve, which represents a low minor loss coefficient. This means the piping system has fewer restrictions, such as fewer valves, elbows, T's, or other fittings. As a result, the head losses are relatively low, and the required system head increases gradually with increasing flow rate. Therefore, this is the flattest curve. Now look at the green curve, which represents a medium minor loss coefficient. As the number of fittings or flow restrictions increases, the minor losses become larger. Consequently, the required system head increases more rapidly for the same flow rate, making the curve steeper than the blue curve. Finally, observe the orange curve, which represents a high minor loss coefficient. This system contains the highest flow resistance due to a greater number of valves, elbows, T's, strainers, or partially closed valves. As a result, the minor losses are the highest, and the required system head increases rapidly with flow rate, making this the steepest curve. If we compare all three curves at the same flow rate, the required head is lowest for the low minor loss coefficient, higher for the medium minor loss coefficient, and highest for the high minor loss coefficient. Therefore, we can conclude that increasing the minor loss coefficient increases the system resistance and makes the system HQ curve steeper. In simple terms, more valves and fittings require more head to deliver the same flow rate, whereas fewer valves and fittings require less